All right, guys, welcome. Today we're going to be talking about specific linear patterns called sequences, develop some key vocab terms, recognize and extend some patterns, and then write rules that allow us to make some predictions about sequences. Now, patterns literally are everywhere in our world. You can see a lot of different patterns in nature, patterns with just figures and shapes and whatnot. And if you guys grew up building things, Legos, anything like that, you probably use some form of pattern to do those. Today we're going to be talking about specific patterns called sequences, and they're essentially just number patterns. And in order to do that, we're going to start with more of a visual prompt. So I want you guys to take a peek at this pattern. Okay, it's just a block pattern. And then attempt to make a response to the question at the bottom there. How many blocks would be needed in stage 30 of this pattern? Okay, so pause the video right now, take a peek at the pattern, and try and predict the 30th stage and exactly how many blocks you would need to have. Again, pause the video to do this. Try and make a prediction. You're probably understanding this or can understand how to do this even easier than you think. But how many of those blocks would you need to complete stage 30? We've got stage 1, 2, 3, and 4. How many blocks would be needed for stage 30? Now I'm going to start with the solution here. So if you haven't paused the video to try this out on your own, please do so now. But this is a visual representation of a linear pattern, okay, with the stage number being our independent, okay, or our x value, call this x, and then the blocks being our dependent, which we'll call this f of x. All right, and you can probably see in the first stage, there are 2 yellows and 3 greens, or one grouping of 3 greens, and then those 2 yellows attached to it, which would be a total of 5 blocks. In stage 2, you can see 2 groupings of 3 greens, and then those 2 yellow blocks as well. So 2 groupings of 3 is 6. 6 plus 2 gets you 8. Stage 3, you've got 3 groupings of green plus the 2. So you got 9 green blocks plus the 2 yellow blocks. That's 11. And what you can see as we continue along with this table is a linear pattern. Okay. Stage 4, you've got 4 groupings of 3 greens, and then plus our 2, that's 4 times 3, which is 12, plus the 2, that's 14. Okay. Now my challenge for this would be to draw stage 0. Okay. And you guys are probably all thinking that if you were to trace this pattern backwards, that the origin of this would be the 2 yellow blocks. I don't have yellow here, so I'm going to draw 2 green ones. But stage 0 would be our 2 yellow blocks that are in each one of these stages. Okay? Our 0 stage would be just 2. And you can see that that fits in nicely with our number pattern. So what's forming over here is what's called a sequence of numbers that is considered arithmetic. It's an arithmetic pattern. And we can write rules for arithmetic patterns really easily by identifying the change or the common difference between our y values. So from 2 to 5, 5 to 8, 8 to 11 is a common change where an m value of 3. Okay, and then also identifying essentially where we started, okay, which was what was consistent amongst the patterns, which is that value of 2. Okay, we're going to call this a b value of 2. So we started at 2 blocks and we increased 3 per stage. The rule for this could be just 3x plus 2. Okay, and many of you guys probably thought of this. At the 30th stage, we would have 30 groupings of 3. Well, that's 90. And then we would also have those 2 that we started with. 90 plus 2 gets me 92 blocks. So if you got 92 blocks for the 30th stage, nicely done. Now, I've got a ton of these. We're not going to spend so much time on the block patterns, but they're going to help us to hopefully understand sequences and understand patterns in general. The part of our brains that controls problem solving, pattern forming, and vision is called the cortex. Cortex is one of the primary portions of the brain that distinguishes humans from animals. So literally, core means from the heart, okay? Part of what makes us humans is the fact that we can identify and extend patterns. So this is a natural part of our brain cycles, okay? Some key vocab, make sure we get this down. A sequence is an ordered list of numbers that oftentimes will form a pattern, okay? This is an example of a sequence. Terms are each number in the list. So this is my first term. This is my second term in the sequence, third term, and so on, okay? So any ordered list of numbers is considered a sequence. And sequences can be determined to be either arithmetic sequences or geometric sequences or sequences that don't really have a specific pattern to them. Okay. So our first step in this lesson is to just try and extend the pattern. Okay, let's look at these examples. Letter A, you go from 12 as the first term, 23 as the second term, 34 as the third term, 45 as the fourth term. The pattern in this case is that the numbers are being added by 11. Okay. The next two terms in the sequence in this situation would be 11 greater than 45, which is 56, and then 11 greater than that number, which would be 67. Okay. Letter B, first term is 1, then we go to a half, then we go to a fourth, then we go to an eighth. If you're mechanical or musical, you probably recognize these units. Whole notes, half notes, quarter notes, eighth notes. Next number would be 1/16th notes, and then 1/32nd notes. Okay, the pattern is the numbers are being divided by 2. Okay, in the musical world, that's called subdividing. If you guys have gotten to that, if Mr. Fromm's taught you that at all yet, but subdivision is kind of a cool concept. And letter C, we go from 4 to 8, 8 to 16, 16 to 32. The numbers are being doubled. You guys probably have noticed. Next number would be 64, and then 128. So the numbers are being doubled. All right. Now, an arithmetic sequence by definition is a sequence in which the difference between terms is constant. This is very similar to a linear equation or linear function. Okay, we can write rules for our arithmetic sequences by using our term numbers as our input, or our x values, and the value of the terms as our output, or our f of x values. Okay? So with this particular sequence, the term number 1 is like an x value of 1. The value of the term is like our f of x. And what we'll try and do is write rules that allow us to extend and make predictions based on the numbers we see in the term. All right. Key concept, rules for arithmetic sequences. You can find any term if you know the first and the common difference. If you know that first number, if you know the initial 2 blocks from the visual example, and you know how the blocks are growing or decreasing, you can write a rule for this sequence. Okay? And you guys have probably recognized this thing, mx plus b. It's something that's come up a lot throughout our units because it's an important concept. Okay, so what we're going to do is write a rule for the sequence that's shown here, and then try and identify the 12th term without having to count up 12 times. So first thing I like to do for writing my rules, which I will kind of give you a little space here, is throw those numbers into a table. So I've got my first term being -3, my second term being -7, the third term, and so on. Okay. The next thing I like to do is I like to leave a space for 0. Okay, because if you notice, the b value is considered the 0 term. Okay, I like to leave that space in my table because it's going to help me to write my rule. Now, the common difference is basically just what is happening to get from one number to the next number. To get from -3 to -7, I'm decreasing by 4. From -7 to -11, another decrease of 4. Another decrease of 4. Not 14, 4. So that's my common difference, is 4. So in this equation, or this particular sequence, common difference is -4. The next thing I'm going to do is identify that 0 term, which would basically be what number is in that spot. So what number decreased by 4 would get you -3, which in our situation would be just +1. +1 decreased by 4 would get you -3. That's my B term. All right? And the rule just takes those two and plugs it right into this equation. F of x is equal to -4x plus 1. All right? Notice how it works for each one. -4 times 1 is -4, plus 1 is -3. -4 times 2 is -8, plus 1 gets you -7. And if you look at the question, it says identify the 12th term. Well, now I'm just going to find f of 12. Because f of 12 would be the value of this function at 12. -4 times 12, and then plus 1. The math on that is -48 plus 1, or -47. Okay, I can find any number in the sequence itself by just understanding basically how the numbers are changing and where they started at. Let's try a couple more. Okay, tell whether the function is arithmetic, and if it is, write a function rule to represent it. So I've got letter A, -7, -3, +1, +5. So I'm going to do my little chart. Leave a space for 0. The first number is -7, second number is -3, third number is +1, fourth number is 5. So those numbers are being increased, it looks like, by 4. This is almost the opposite of the previous rule. Okay, so the numbers are being increased by 4. My 0 term, or my value that would come right before the -7, is -11. So I've got m value is 4. My b value is -11. My rule then is f of x equals 4x minus 11. Okay. Right now we're just writing the rule. We don't have to apply it to anything. Just get a little practice with that. Letter B. Let's make our table first. So we got our x and then our f of x. Leave a space for 0. The first term in the sequence is 3. Second term is 8. Third term 13, so on. Fourth term is 18. You guys probably have caught on to the pattern at least. Remember, a pattern and a rule are different. So from 3 to 8, that's an increase of 5, increase of 5, increase of 5. My 0 term, or my value that would come right there, is going to be 5 less than 3, which would be -2. So I've got an m of 5. I've got a b value of -2. My rule then is f of x equals 5x minus 2. All right? Notice how it works for each one. 5 times the first term, minus 2. 5 times 2, the second term, minus 2. 5 times 3, the third term, minus 2. 5 times 4, the fourth term, minus 2. Okay, pretty easy once you understand what each of those numbers represents. Okay. Next question. Identify if the sequence is arithmetic, and if it is, write a rule that describes the sequence and then find the 25th term. So remember, arithmetic just means the numbers are increasing or decreasing at a consistent amount, or they're adding and subtracting. Another way to think of it is arithmetic starts with A, think add, subtract. Okay? So with A, 13 to 16, 16 to 19, 19 to 22, those numbers are definitely increasing by 3 per term. So let's even just do the kind of the lazy way of doing it. I'm not going to make a full-fledged table, but I'm just going to put 0 here, first, second, third, fourth, and then I'm going to make my table out of this. I know. Mathematicians can sometimes be lazy. You guys are all mathematicians. It's okay sometimes to be lazy. So when you think about it, first term with 13, second term with 16, the 0th term would be the number that comes right before 13. In this situation would be 10. That's our B value. That's our initial amount. Okay. Our M value is what's happening to the numbers. So 13 to 16, 16 to 19, 19 to 22. M value in this case is 3. So increasing by 3 per term, starting at 10. Our rule then is 3x plus 10. Now we're not quite done because it does say to find the 25th term in the sequence. You can definitely, if you want to, extend this and go, the 5th term is 25, the 6th term is 28. If you want to do that 25 times, that's great. But think about it, guys. We've added 3 25 times. We might as well just take 25 times 3. Okay, we didn't start at 0, we started at 10, so we might as well just do the math this way to find the 25th term. Okay, 3 times 25 is 75, 75 plus 10 gets us our 25th term. We're done. That's it. Okay. Now, letter B. I see a pattern, okay? From negative 12 to get to 24, that multiplied by negative 2, multiplied by negative 2, multiplied by negative 2. So there is a pattern to this. It is not an arithmetic pattern, okay? If you have to multiply or divide to get from number to number, this is called a geometric pattern. Okay? Geometric means you're multiplying or dividing to get from number to number. And while there is a way to write a rule for this, that'll be for a different lesson after we talk a little bit more about some of the rules of powers. So if it's geometric, for the time being, just identify it as so. Okay, just say this is geometric and call it good. All right. Yeah, that's basically it. We could practice and continue. Common difference here, number to number. These numbers are growing, it seems, by 4. And the 0 term, the value of y when x is 0, or the value of f of x when x is 0, in this case would be negative 16. The rule for this would be 4x minus 16. Okay, we could continue on. The second one would increase by 3 per term, starting at 19. So 3x plus 19 is the rule for that one. Okay. But mostly I'd just like you guys to have some time to practice with this and get dirty with the content. So that'll be the end of the lesson for today. Get started with your homework.